this module we are treating the basics of particle acceleration and detection method. In this second video we treat the acceleration and focusing mechanism inside accelerators. After watching this video you will be able to answer the following questions. What are the main components of an accelerator and how do they work? And how does a complex of accelerators like that at CERN work together to achieve the highest energies and highest intensities? Inside an accelerator, particles move in an evacuated tube, and this is to prevent them from interacting with air molecules and lose energy or be transformed. Even if they don't, we still need to supply radio frequency acceleration even in a storage ring if we want to keep the beam energy constant. This is because an accelerated charged particle loses some fraction of its energy in the form of radiation by emitting photon. This process is called Bremsstrahlung. The same process produces photons in an X-ray tube. In such a tube, the electron cathode ray beam is stopped by an inclined water-cooled target. The energy of the electron is typically 10 kV. They thus yield X-ray photons of a comparable energy. But also lateral acceleration creates Bremsstrahlung, namely synchrotron radiation. For relativistic particles, the loss power per turn, P, is proportional to the force power of the relativistic factor gamma and inversely proportional to the radius of curvature ρ. It is large for light particles circulating in small orbits. This loss must be replaced constantly to get a stable beam in an orbit of constant radius. But synchrotron radiation is more than a nuisance. One uses it to produce monochromatic photons. The Swiss light source at the Paul Scherrer Institute in Villingen is a source of high brightness light based on an electron synchrotron of 2.4 gigaelectronvolts. Its beam lines are used for research in material science, biology and chemistry. The accelerating electric field is generated by a vacuum tube amplifier, the klystron. An intense electron beam is accelerated, then bunched in a resonant cavity. In a second resonant cavity, the electron kinetic energy is extracted in the form of a radio frequency wave. Modern klystrons have normally several such amplification stages. The beam is held on a circular path by dipole magnets. The transfer focusing of the beam is done by quadrupole magnetic fields. A low quadrupole component is normally present even in a dipole magnet. The focalizing forces come from a slight horizontal component of the magnetic field, which changes sign as one passes from below to above the orbital plane. By alternating this quadrupole configuration with one which is rotated 90 degrees, a focalization is obtained in both horizontal and vertical direction transverse to the beam. Magnets with dipolar and quadrupole fields thus accompany the accelerator ring. Two coils create a dipole field, four create a quadrupole field as shown. Today these coils are normally superconducting to minimize resistive loss. But focalization is also needed in the longitudinal direction. The reason is that the particles must arrive synchronously to acceleration points. Thus they are injected in short packets. If they arrive at radio frequency resonators on the increasing slope of the electric field, their phase remains stable. A particle arriving with a slight delay compared to the ideal phase will see a field that is stronger than the average field. A particle with a slight advance will, on the contrary, see less accelerating field. In this way, the particles will automatically oscillate around the ideal phase. We can lower energy losses from synchrotron radiation by increasing the radius of curvature ρ, weakening at the same time the dipole field. Asymptotically, we can let ρ tend to infinity, resulting in a linear accelerator. Almost every accelerator complex begins with such a device. Much of the vacuum tube, which contains the beam itself, is a resonance structure of radio frequency with a traveling electromagnetic wave. Between the resonant cavities there are spacers made of conductive tubes. Their length must follow the velocity of the accelerated particles, such as it should be equal to the velocity times half the period of the radio frequency. It is also necessary that when passing in a shielded portion of the cavity, the electric field has the desired sign and value. Once the velocity of the particle is sufficiently close to the speed of light, the spacing becomes constant. Today's powerful accelerators are mainly working in synchrotron mode. The most powerful, the Large Hadron Collider, has been in operation since 2008. It is part of a complex of accelerators to obtain maximum energy luminosity. In 2011 and 12, the energy per proton per beam was 3.5 tera electron volts. In 2012 was raised to 4 tera electron volts, and after a technical interruption that started in February 2013, the operation resumed in 2015 with 7 tera electron volt per beam. This corresponds to the impressive energy of 1.12 microjoule. The path of particles through the complex is shown in the short CERN video 3.2a. In the next video, we will visit CERN to discuss the key components of the LHC with Professor Tobias Golling of University of Geneva.